So now we're going to be looking at internal combustion engine cycles. So in this course, we're going to look at three different cycles. The first one being the diesel cycle. So this is used in low-speed diesel engines, the ones that you'd find in a ship or on a large truck that's running at low speeds. So that's the diesel cycle. All right, and then the second cycle that we're going to look at is called the dual cycle. And this one is a combination of the diesel and the Otto cycle. All right, so this cycle is usually used in modern diesel engines. So it also uses diesel as its fuel, but it's used in modern high-speed diesel engines. And then the third cycle we're going to look at is the Otto cycle. And the Otto cycle is used in petrol engines, where the air and the fuel is mixed before compression, and then there's a spark plug that creates a spark and causes the ignition to take place precisely. All right. So before we begin looking at the diesel cycle, I just want to point you to this document that I've put on Blackboard about the gas processes. Now, you guys know this stuff already. So this is just a short summary of the processes. And you're going to see these processes in the cycles. So you need to know how the pressure volume diagram works, how the TS diagram works, right? The pressure volume and the temperature entropy diagrams work. And you can see in this table here, it nicely shows you how to draw them, and it shows you the work formulas, the internal energy formulas, and the heat formulas, right? And so what I'm going to do is I'm going to leave that for you guys to go through. Very important though, at the bottom here, I just want to take you to this. At the bottom here, so this was derived, but it should have been derived previously for you guys. But I'm not going to derive it for you because should be prior knowledge. But this is the polytropic laws, okay? So for a polytropic process, where all of the pressure, the temperature, and the volume changes, these are the laws for that, okay? So you need to know that, and you get this on your formula sheet, thankfully. Then you get the adiabatic laws, and you'll see it looks exactly the same, but N is just replaced with gamma, all right? So that is for an adiabatic reversible process, right? So this is ideal, okay? You can't get this in reality, all right? So on the formula sheet, you'll have the polytropic laws on your main formula sheet. Let me just show you quickly. Right in the beginning here. So you have it here. And for the adiabatic laws, you just have to change N to gamma. All right. And yeah, over here are some more useful formulas that we're going to be using as well. All right, on the formula sheet. So please get familiar with those. All right, so let's look at this diesel cycle now. All right, so there is inside of your diesel engine. Yeah. So first of all, we have the intake. So you can see here, the valve opens up, the piston is going down, it's sucking in free, or I should say it's sucking in fresh air into the cylinder. Then on the compression stroke, as the piston starts moving up again, it starts compressing that fresh air. And you all know that when you compress a gas, the temperature increases rapidly. All right. So they're compressing this air into a very small confined space as it reaches top dead center. And because of that, the fresh air becomes very, very hot. All right. And now on the power stroke, you see over here at the top here, there's a fuel injector. And this is connected to a diesel pump. It pumps the diesel in at a higher pressure than the air is in the top of the cylinder here. It has to be at a higher pressure, otherwise it won't go in. And as that diesel goes into that small confined space where that very highly compressed, very hot air is, it causes the diesel to start burning. So there's no spark, there's no flame in there, but because purely of the high temperature, that fuel starts to flash, to burn. All right. And when it starts burning, initially it starts burning at constant pressure or relatively constant pressure. So this piston starts moving down slightly. The volume starts increasing very slightly. And because of that, it's burning under constant pressure. Then what happens is all that compressed air now is getting very, very hot. It was hot in the beginning, but now because of that burning fuel, it gets extremely hot and it rapidly expands and it pushes down this piston. All right, so that's your power stroke, and that's where you get your power from. Then afterwards, you just got this burnt exhaust gases in here, and the piston moves up again, and it pushes those exhaust gases out, along with all the wasted heat. Okay, so that heat that goes out there, you can't do anything with. It's gone. All right, so that is the cycle. So again, brings in fresh air, compresses that fresh air very tightly. The volume is very small. The heat gets it rapidly increases. Once you inject that fuel at a higher pressure into that little space, it burns because the air is so hot in there. It burns initially under constant pressure, and then the rest of the air starts expanding rapidly and pushes down that piston. And then obviously the exhaust gas gets ejected out of the exhaust port. All right. So that is the cycle, and that's what's happening basically inside of a diesel engine. But now we're going to look at the cycle itself. Now you guys need to remember that this is the ideal cycle, so this is not reality. You're going to see there's something missing on the cycle, and it's the intake and the exhaust strokes. So the intake and the exhaust, that's missing on this cycle because it's ideal. Okay. So in the beginning, we are at 0.1, right? So you can see the volume is at its greatest, okay? So that's just before the compression. So it's the intake, it's pulled the air down. So once it's at the bottom and it's full of air now, that's position 1, right? So it's pulled in the air, and now what's going to happen is it's going to compress. So it's going to compress that air, and you're going to see the volume's going to decrease, and as the volume's decreasing, the pressure's increasing. Okay, and that compression, it's an ideal process. So it's adiabatic. Okay, so it's not reality, it's adiabatic, and you're going to see it's even reversible. So if you look on the side here, we also have the temperature entropy diagram, and you see here, so position 1 is that position 1 over there. So as it's increased, compressed adiabatically, you can see the temperature rises like we expect. The temperature rises, but the entropy remains constant. Okay, so it's an ideal process. The entropy is remaining constant. Even though it's happening really, really fast, this entropy is remaining constant. Okay, and then at the top here now, from 2 to 3, this is where the fuel is injected into that compressed air, into that hot compressed air, and it starts burning under constant pressure. Remember I said as it starts burning, it starts pushing that piston down a little bit so that the volume is slightly increasing. You see the volume is slightly increasing, but the pressure is remaining constant. Okay, and then once that compressed air with that burning fuel gets extremely hot, that compressed air now gets so much energy that it starts expanding, and it expands now adiabatically. So it expands adiabatically, and that's your power stroke there. Okay, and then at 0.4 now, it's expanded, and from 0.4 to 0.1, the leftover heat that is in that cylinder is now rejected. So you can see there I've drawn these red arrows here. The leftover heat that is lost, that is wasted, that usually would come out the exhaust valve is now ejected. But in this case, it's a ideal cycle, so you won't see the intake and the exhaust stroke. Okay, So just keep that in your minds. Okay, so first of all, the adiabatic compression and the adiabatic expansion, which formulas are related to that? So if you go to your formula sheet, it's these ones here that we just looked at, right? So that's for a polytropic process, but it's adiabatic, so we need to change the ends to gamma. Okay, so if we look on this cheat sheet that I gave you guys online, you can see over here that's the adiabatic laws. Okay, so we're going to use these these relationships between temperature and volume, volume and pressure, temperature and pressure. We're going to use these to be able to calculate the missing information. So we're going to say they'll give us information here at the beginning, and then to calculate maybe what the pressure is or whatever at point 2, we're going to use those formulas. Okay, then we look at from point 2 to point 3, and that is a constant pressure process. Now, you will remember there is a formula that looks like this. P1, let me get that in camera there. P1 V1 over T1 equals P2 V2 over T2. Okay, and that formula, you need to know that out of your head already. But that is the combination of Charles's law and Boyle's law. Okay, so constant volume and constant pressure processes, you link them together, or you substitute the two together, and you get this formula. And this is when all of the pressure, the volume, and the temperatures are changing. Okay, so that's not on your formula sheet, but you need to know that. So if we look back at the pressure volume diagram, points 2 to 3 is at constant pressure. That's when the fuel is being injected into the cylinder and it's starting to burn. So it burns at constant pressure because that cylinder starts expanding very slightly, all right? So it burns at constant pressure. Now, if we look at the formula that we just looked at, P1 V1 over T1 equals P2 V2 over T2. Of that formula, what can be cancelled out? Obviously, it's the pressure, eh? So P1 and P2 can be cancelled out. So for this section, we actually need to have, we should say V2 over T2 equals V3 over T3. All right, so that's for this constant pressure part here. Sorry, it was out of camera. V2 T2 over V3 over T3. All right, so that's for the constant pressure portion of the cycle. Then it expands adiabatically again, and remember, same thing. I'll repeat it again so you don't forget. It's the same adiabatic laws from the formula sheet. Remember, N gets substituted with gamma. Okay, so that we're going to use for working out positions or points 3 to 4. All right, so that's adiabatic expansion, and that's the expansion of the air. That's like super hot now. Then we go down to position 4, and to get the points or the pressures, temperatures, and volumes from 4 to 1. Now again, what type of process is this? So if you just look at the cheat sheet again, right? It's a constant volume process. Okay, constant volume process. So what's going to be cancelled out now from this formula? So over here we're going to just have P4 over T4, that's there, equals P1 over T1. All right, so we're going to cancel out the volumes now because it's a constant volume process. Okay, so that's it. You really, they're going to ask you to just figure out all these points, and you just need to know this formula. P1 V1 over T1 equals P2 V2 over T2, and you need to know the adiabatic laws. Okay, and that's it. So in the next video, we will do a problem working out the thermal efficiency of a certain engine. All right, so we will do that in the next video.